Salt. 200 million years it took to create me. So who am I? What am I for? You tell me.
So if there wasn't salt, there wouldn't be any taste in the food. Chips.
When it's been snowing, put the salt on the floor.
Salt consists of two ions, a positive sodium ion and a negative chloride ion, which come together to form what's called a lattice structure.
You definitely need salt to survive.
My mum used to use salt to clean our teeth.
For food and stuff.
You can use it with other chemicals to produce products.
Mostly chips.
Chips.
Is that all? You owe half your world to salt, your very life. 200 million years to give you all you need and cherish, all from a grain of salt, torn from the crust of the earth.
This huge lump of rock salt is actually millions and millions and millions of years old, and it's not anything like the salt that you put on your chips. Does anyone know where it comes from? No? It's mined underground in Cheshire, hundreds of feet beneath the fields. And it was actually made, believe it or not, from seawater, and was originally, millions of years ago, part of a shallow sea which evaporated slowly and allowed the salt to form as crystals, eventually to become part of a rock underground. Now, what I want you to tell me is how you can turn that into salt like this, something that you could eat or put on your chips. Now, what's the first thing that you would do?
Crush it.
Crush it, right. First thing is to crush it up. Now, this is actually being crushed by the firm who actually owns the salt mine. And you can see what it's made of. There are brown bits, like that. What do you think the brown bits are? Bearing in mind that this is rock salt. What do you think the brown bits are?
Bit of the rock.
That's quite right, yeah. How about the clear bits?
The salt.
That's right. But is this crushed stuff used for anything before you actually take away the rock? Have you ever seen this stuff being used for anything at all? Not at all. Can you remember a really bad winter? This is actually used on the roads in winter. This stuff is, when you say grit on the roads, what it actually is crushed rock salt. Now, the salty bits help to melt the ice, and the rock bits actually help the car tyres grip the road. Anyway, back to turning this into that, salt that you can put on your food. What differences are there between the rock and the salt that we could use to separate them?
The colour.
Right, you could separate them by colour. What else could we do?
Putting it in water.
Right, how would that help?
Because all the salt would start to come off it.
Right, now, what's happened to the salt? There's a special word for it. What does the salt do that the rock doesn't do?
Dissolve.
It dissolves, right. So, the salt has dissolved in the water. You've got salty water with bits of rock at the bottom. Can you imagine what would happen if you poured this through a piece of paper towel? You will find it would sieve out the dirt and let the salt with the water go right through. Right. Do you understand that? Now, the next thing you've got to do is try and get the water away from the salt. How could you do that?
Let the water evaporate from the salt.
Exactly. Now we're going to use the ideas that Anne-Louise, Justin and Leon suggested to try and separate the salt from the rock using the equipment that we've got at the back of the room. What you're going to do to start with is you're going to weigh out 20 grams of crushed rock salt into one of these plastic cups. Right, how much water do you need? So I'll fill it for you. Tell me when I'm getting to the top.
Yeah.
Right, check that. Right, okay, we'll give this to you now. Can you get that one from behind you? Yeah, thanks a lot. Yeah, pour that bit out. Pour that bit out of that bucket.
Rock salt and water mixed together and poured through a paper filter produce clear, salty water called brine.
Ours is well cleaner than yours.
Next, you need about a teaspoonful of salty water and then some gentle cooking.
Thank you very much. What do you think's going to happen?
Let the water evaporate and you'll just be left with the salt.
That's right, yeah. Just like a puddle drying up when the sun comes out. Can you imagine getting salt from the sea by leaving it out to evaporate?
In this part of Australia, they can evaporate millions of gallons of salt seawater each day, just using the power of the sun. It looks like snow, but it's all salt. There isn't enough hot sun in Britain to evaporate salt mountains like these straight from the sea. In this country, giant cooking pots in a factory are filled with salty water pumped from underground salt beds. The salty brine is boiled up until it evaporates, making steam and eventually salt crystals that sink to the bottom of the pot. The waste steam is piped on, and the whole process is repeated again and again to make huge quantities of salt.
Right, now then, can you see what's happened? What is there now?
The salt.
Yeah, that's right. So, the question is, do you think you need salt to live?
No.
You don't. When you sweat, for example, you can see the salt actually comes out on your skin in the perspiration. So you were losing salt then, so you have to replace that salt, and without the salt, you won't be able to live. Shall I show you how much salt is in one of you? That's about 90 grams of salt, and that's how much is in you. How much do you think is in an adult?
Twice.
Twice as much.
180 grams.
180 grams, twice as much, right. That's about 3 times as much. That's how much salt is in someone like yourself. And you do need the salt to live.
There's enough salt here for about 300 million plates of chips. They've been making salt at this site in Cheshire for over 100 years. It's the biggest salt factory in the world. They make 1 million tons a year for all over the world. This is the salt we eat with our food. But other processes can make different kinds of salt. And under the microscope, there's a whole new world to explore.
We take the magnification down. This is the magnification that's indicated. It's only times 10. And there's a piece of rock salt. Now, you've seen a big piece this morning. This is just a tiny piece. Now, further round on the sample, we've got a piece that I took from one of your crystallising dishes. It's a square, it's cubic. If we take the magnification higher...
This special microscope can enlarge a picture of a salt crystal 10,000 times.
These are layers of salt. We've also on this sample got a different type of salt again. This is dendritic salt, which is made with an additive so that it's very, very porous. It's got holes in it. And the water goes into the holes to make it dissolve quicker.
But you only know half the story. I have great power to create other things in other places. Magical transformations you've never dreamed of. There's so much more to know. So much more. $200 million years to create me from sea and sun and sand, from the depths of the earth. I'm the salt of the earth.
Okay, this is the mask that you'd need to wear if we had a fire in the mine. Just open your mouth, put it in just like a snorkel. So that's it, bite on that. Okay. The next day, just nod your head.
These Liverpool students have made a journey 200 metres underground to a prehistoric seabed. Cheshire's salt mine is a honeycomb of caverns and 100 miles of tunnels and roads.
When I first come down here, I thought that you might have to crawl around in parts, that it'd be so small like, but here it's massive.
A century ago, they used sweated labour to dig out the salt. Now it's down to mechanical muscle. Working with an armoury of high-technology equipment, they can cart and drill and blast up to 2 million tonnes of rock salt a year.
The patterns that this machine makes on the walls, it's like something out of a science fiction movie or something. And the actual machine itself, it's a bit terrifying, you know.
This one machine can claw out 100 tons of rock salt an hour, tunnelling still further into the mine, with cutting accuracy guided by laser and monster teeth armoured with specially toughened metal.
Anybody question? Don't anything?
How many men operate the machine?
Just one man operates the machine. He deposits the rock, the cut rock, at the back of the machine, and we have a man at the back that actually picks it up on a Caterpillar loader and takes it away. We have space.
The machines, they're a lot bigger now than I thought that they were. I mean, I thought there'd just be a couple of small ones, but with this big one, it's frightening. I wouldn't like to be here on my own.
I thought it was eerie. Spooky. It's a lot colder than I expected then.
It doesn't seem like you're 600 feet down. It just feels like you're in a large room.
It's just like an underground city. People could live here. It's massive.
Above ground, some of the fine crushed rock salt will be used as a fertilizer for salt-loving crops like sugar beet. But the rock salt mountains are stockpiles for winter roads. Adding salt lowers the freezing point and melts ice at lower temperatures than normal. No salt mountains here. These pipes and valves are the only visible sign of the chief method of salt extraction, solution mining. From wellheads like these, pipelines are drilled through the earth hundreds of meters down into the Cheshire salt beds. Water is pumped down from the wellhead, dissolving the rock salt to make brine, and gradually carving out huge cavities or boreholes in the salt beds. The brine is pumped to the surface, leaving most of the rock and grit behind. There was a time when salt mining was less than popular. Before safe mining techniques were developed, surface soil wasn't always properly supported, and sometimes the earth moved in spectacular ways. Nowadays, sophisticated remote control systems monitor every aspect of solution mining, checking underground water levels or controlling the flow of brine from the wellheads across the Cheshire countryside to a chemical site on Merseyside. This is where the last of the impurities from the rock salt are removed, ready for pure brine to be processed into the salt we eat, or for brine to be used as the basic ingredient in the making of a whole range of chemicals for industry.
I'm George Baxter, and I work with chemicals that come from salt. This is brine from the underground salt beds. Now, it may just look like ordinary salt water to you and me, but in fact, it's very important to us here, because with a little bit of scientific magic, we can turn it into three things that we need. Two of them are actually invisible, but you just have to use your imagination. The first is chlorine. We have a short way of writing that. Chlorine is very important. Not only is it used in medicines and also in a lot of the plastics which we produce, but it also helps to keep our drinking water clean and free from germs. The second, that's sodium hydroxide. Now, sodium hydroxide is the chemical name for it, but try to think of it as the chemical which makes paper stronger, which produces washing up powders, and the soap which we use to clean our hands. And the third, well, that's hydrogen, which can be used as a fuel, for instance, on the space shuttle, and also on this site. And surprisingly, it's also used to affect the texture of margarine, whether it's hard or whether it's soft. And all of this from ordinary salty water with a little bit of scientific magic. But of course, making the magic happen, well, that's another story.
Cool. Just imagine, all that can happen because of me. Scientific magic, he said, from common salt. Fancy that now. I'm not just common salt. I'm sodium chloride. Yeah, that's my proper name. I'm part of very important chemistry.
What we're talking about today is electrolysis of brine, which is salt solution. That is sodium chloride, which is salt, dissolved in water. Now, can anybody tell me the formula for sodium chloride? Yes, Jenny?
NaCl.
NaCl, correct. Now, in fact, it's made up of two ions, a positive sodium ion and a negative chloride ion. Those two ions, being of opposite charge, hold the structure together, and it's quite difficult to separate them. But one way you can separate them is by dissolving the salt in water. Now, the number of ions you get from water is only very small, but nevertheless they are there. So present in the solution, which is in the beaker in front of you, you've got 4 ions. 2 positive ions, the sodium ion and the hydrogen ion, and 2 negative ions, the chloride ion and the hydroxide ion. During electrolysis, we have, of course, got 2 electrodes, the positive anode and the negative cathode. And all we have to remember, of course, is opposite charges do what? Can anybody tell me? Yes, Susan?
Attract.
Attract, yes, Susan, they will. Opposite charges attract. Okay.
The theory is a kind of scientific recipe, and the recipe must be totally clear for a proper understanding of the practical chemistry, all set up ready on the lab bench.
Right, now, before we start the experiment, would you like to put the goggles on, safety goggles on, then put the switch on, and then have a look. You should see the bulbs lit up, just to check the circuit's working. And if you look at the 2 electrodes, you should be able to see gas bubbles coming off from both electrodes. First of all, cautiously have a smell at the top electrolysis cell. Now, is there any smell there that you recognise? Yes, Lisa?
It smells like a swimming bath, the chloride.
It does indeed, doesn't it? The chlorine smell you get from the swimming baths, yes.
Passing an electric current through salty water has transformed brine into 3 new chemicals. But what's actually happening in there?
I did find it hard to understand, but what comes off at the negative cathode is hydrogen gas, and what comes off at the positive anode is chlorine gas.
The solution that's left is sodium hydroxide. It's quite simple, really.
Electrolysis is more than just an academic exercise. It's an essential part of producing bulk chemicals for industry.
When you come onto a commercial scale, the difficulty is that the chlorine and the sodium hydroxide react to form other chemicals, sodium hypochlorite, salt and water, which you don't want. Therefore, must have some way of keeping the 2 chemicals apart. Now, the first of these is the mercury cell. And what we've got there is a cell containing a titanium anode. Only one is shown here. There are more than one in practice.
Inside the cell, a row of metal anodes sits above a stream of mercury. The mercury is the cathode. Brine flows through the cell, and electricity goes from the anodes through the brine to the cathode. Negative chloride ions in the brine are attracted to the anode. They each lose an electron and become chlorine gas, drawn off at the top of the cell. The other reaction is that positive sodium ions are attracted to the mercury cathode. They each pick up an electron and form an amalgam with the mercury. This sodium-mercury amalgam flows out of the cell and down through a bed of graphite. It reacts with water to produce sodium hydroxide, also known as caustic soda. Hydrogen comes off as a gas, and the leftover mercury is recycled. Huge mercury cell rooms like this produce high-quality chemicals, but mercury is a poison, and even the smallest amount of toxic waste must be managed. Another kind of electrolysis cell was developed that didn't need mercury.
Now, the second way of overcoming this problem is using the diaphragm cell. This, in fact, contains a diaphragm, as the name suggests. The diaphragm will allow ions to pass through it, but will not allow gas bubbles to pass through it.
This diaphragm is attached to a metal grid which acts as the cathode. Together, they slot into a toast rack of titanium anodes. It's the diaphragm that makes chemical separation happen.
And there you can see the brine being fed out the top, chlorine coming out there, hydrogen there, and the solution containing sodium hydroxide there. Remembering that solution is not pure, it contains about 1% sodium chloride as an impurity.
With every development, the aim is to produce the best quality chemicals using less energy. Another kind of electrolysis cell has achieved that. It's called a membrane cell.
This is fairly similar in some ways, but the plastic membrane in between the anode and the cathode compartments is a very special one. It will only allow sodium ions to travel through it. If you remember, the problem with the diaphragm cell was that chloride ions were to travel through as well, unwanted chloride ions. This special membrane will only allow sodium ions, and sodium ions only, to pass through it. It is ion selective.
The polymer used for the membrane has increased efficiency, but so has the total cell design and the materials used. The membrane cell is a success story. But in these ICI laboratories, they're continually measuring cell performance, like these checks on a prototype of the next generation of membrane cell, to test the quality of chlorine gas being produced.
So in conclusion, you can see that this membrane cell is more efficient than the other two. It uses less energy. The products that it produces are pure, and there's no problem with mercury or any other substances like that.
A century ago, the invention of industrial electrolysis changed our world and our lives. In the choked slums of Victorian Britain, death by typhoid and other waterborne diseases was common. In London, about 1 in 7 children would die before the age of 12. The chlorination of public water supplies helped save millions of lives. Chlorine-based disinfectants can kill 99% of bacteria, and their introduction revolutionized hospital care. Electrolysis and the ability to produce huge quantities of salt-related chemicals stimulated mass production this century to provide for the needs of a growing consumer society. For the chemical industry, ever-increasing demands for product require skilled and careful management.
We produce huge amounts of chemicals here. I mean, if you can imagine, it's about 1 million tonnes of chlorine a year, and just over that, about 1.1 million tonnes of sodium hydroxide, together with around 30,000 tonnes of hydrogen. So you can imagine, like any business, that actually has to be managed and marketed very well. I can give you an example of that. Suppose one week we need more chlorine for plastic production. Then we will produce something like 20,000 tonnes of chlorine. We'll also produce round about 20,000 tonnes of sodium hydroxide. If the demand for sodium hydroxide, however, is only 15,000 tonnes, then we have to ask, what do we do with that extra 5,000 tonnes? And in the opposite situation, where the demand for sodium hydroxide has increased, we also produce an extra 5,000 tonnes of chlorine. So what do we do with that excess? Now, this is where the management and the marketing skills come in, and the planning skills, that we have to look for markets not only within ICI, within our own plants, but elsewhere, possibly Europe and elsewhere around the world. And if we get that wrong, that can be very bad business.
Yeah, and you thought salt was just for chips. No, it's quite a responsibility, this salt business. I was once a living sea. 200 million years it took to freeze an ocean into solid salt rock. Now I'm magicked by science into another form.
Chlorine produced by industrial electrolysis has brought great benefits. The water we drink is safe because of it. In hospitals, bacteria are killed by chlorine-based disinfectants. In the Third World, insecticides are protection from the scourge of disease. The saline drip of salt is held in a bag of PVC, itself made from chlorine. Chlorine married to organic chemicals like ethene, also known as ethylene, becomes a solvent for degreasing machine parts, or for dry cleaning, or for making paints. It's used with other chemicals to make household bleach, or for treating sewage to keep our beaches safe. The other chemicals produced by electrolysis have other uses. Sodium hydroxide, an alkali, goes into the manufacture of soaps and oven cleaners. It's used in paper making for strength and to stop paper yellowing. And it's used in the making of textiles. Hydrogen can be used as a fuel. On this chemical site, it helps supply some of the huge amounts of power needed. And hydrogen can change molecular structure, texturing margarine, for example. By a different set of chemical reactions, brine helps to make another important product, sodium carbonate. That's an essential ingredient in the making of glass. Salt chemistry and electrolysis of brine are the roots to so many of the ordinary things of life, and the extraordinary. From the space shuttle to a premature baby fighting for life, both at some point are dependent on the benefits of this science. But is there a price society is unwilling to pay? Certain chlorine compounds can damage the Earth's ozone layer, letting through more ultraviolet rays than before. Over the last few years, the chemical industry worldwide has had to take painful stock of itself, and chlorine has been at the heart of the environmental debate. United by their concern for the future, world governments have drafted new measures to protect people and a planet at risk. It was a scientist who first identified the hole in the ozone layer. And society looks to science to solve its problems. But should it all be left to the scientists?
No, it's everyone's responsibility to do something about the environment.
My own personal concerns are that we all have to realise that the environment isn't just some huge rubbish dump that we can throw things into and forget about them. What we have to work towards is eliminating pollution at source. And it's not only good environmental sense, but it's very, very good business sense for all of us, because every bit of pollution is waste.
Solvent waste is a case in point. The engineering industry has traditionally relied on solvents, from degreasing machine parts to cleaning delicate electronic circuitry. Some solvents are part of the family of CFCs that can cause damage to the ozone layer, and careless handling lets more solvent escape. New technology has been developed to trap solvent vapor inside a closed unit. It can reduce solvent escape by 80%. Now it's up to industrial users to adopt technology tailor-made for them. One particular CFC is used as the coolant in refrigerators. When old fridges and freezers are scrapped, if the CFCs aren't recycled, they can escape into the atmosphere. It's the chlorine atoms breaking away in the upper atmosphere and reacting with ozone that can cause thinning of the ozone layer. ICI invested millions of pounds and committed hundreds of scientists, engineers and commercial experts to producing alternatives. For many, it was the challenge of their lives.
The challenge facing ICI and the team here and on the plant and on the pilot plant was an immense challenge. To do in 4 years what usually takes 10 or 15 years to do. It's not just identifying what the new chemical might be to replace the CFCs, which we have to phase out, but to find out if we can make it, to look at the toxicology, to check if it's safe for people to use, to check if it's safe for the environment, to make sure the scientists are working with the engineers who are working with the commercial people to actually bring the product to the marketplace in a very short period of time.
But the route to invention is never simple. One problem in the development stage involved the lubricant that, like the old CFC, plays a key part in the refrigerator cooling system. They had to test whether the lubricant and the new compound were chemically compatible.
This is the old CFC, and when added to the old oil, they mix very well. When we take the new chemical, HFA, and mix it with the old oil, as you can see, they just don't mix. And this is important in that some of the oil goes round the system with the refrigerant gas, and we need to make sure that that oil returns to the compressor so that the compressor is not starved of lubricant and fails. We therefore had a lot of work on our hands to come up with a new oil that would mix with the new refrigerant, and finally we came up with the solution.
So, with ingenious science, the old CFC molecule, with its unloved chlorine atom, is being replaced. This is what the new ozone benign compound looks like. there's not a single atom of chlorine in this molecule. Although chlorine is still an essential part of the complex chemistry to create a product that has made scientific history. But the story doesn't end there.
The development of this new chemical is just one of a whole family of new chemicals to replace the CFCs which we have to phase out. But we are continually improving our products and developing our products so that we get the best possible ones in the marketplace.
It's the same pattern of development with the new membrane cell. Its fuel efficiency and purity of product mean that it's already replacing old mercury and diaphragm cells in many countries around the world. But the research goes on, and they're continually testing experimental versions of the membrane cell to improve performance still more.
Have a look at temperature.
These temperature and voltage checks are part of research to investigate the long-term effects of impurities on cell performance. And research has already made it possible to extend the range of chemicals produced by electrolysis. A miniature version of the membrane cell is being used here to breathe new life into chemical problem solving. Steve Forsyth is using electrochemistry not to produce product, but to invent new chemical processes.
The FM01 is a smaller scale version of the FM21, so that we can do experiments in the laboratory on, say, 10 to 100 gram scale and be able to accurately predict what will happen on the full-size plant. And the advantages of using the electrochemistry are that we've got an electron, which is very cheap and versatile and clean reagent to do some fairly unique chemistry.
Steve's work, like so much of today's science, is partly driven by a serious concern for the world we live in.
We feel that we have some responsibility, as is the whole of society, to make sure that the environment in which we live is a happy and healthy one, and I'm sure the chemical industry is helping to do that.
As a scientist, I enjoy exploring and understanding the world that we live in. But I think that has to be done in the context of the moral and ethical values that society imposes. And certainly as a Christian, I believe that we should be good stewards of this earth, and we should explore it and develop it in many ways, but not abuse it. It's got to last us a long time.
200 million years to create me. Just think what the future might bring from salt.